All right, so we're going to be doing section 1.6 of Blanchard's differential equations. So let's just get into it. All right, we're going to be doing all the exercises too. All right, given a differential equation, we can get an idea of how solutions behave by drawing slope fields and sketching their graphs, or by using Euler's method and computing approximate solutions. Sometimes we can get explicit formulas for solutions and plot the results. All of these techniques require a bit of work, either numerical or analytic. In this section, we consider differential equations where the right-hand side is independent, so autonomous differential equations, independent of t. The word autonomous means self-governing. Roughly speaking, an autonomous system is self-governing because it evolves according to differential equations that are determined entirely by the values of the dependent variables. For autonomous differential equations, there are qualitative techniques that help us sketch the graphs of the solutions with less arithmetic than with other methods. All right, so remember, autonomous equations are ones that just depend on the dependent variable. In other words, the rate of change of the dependent variable can be expressed as a function of the dependent variable alone. Autonomous equations appear frequently as models for two reasons. First, many physical systems work the same way at any time. For example, a spring compressed at the same amount at 10 a.m. and 3 p.m. provides the same force. Second, for many systems, the time dependence averages out over the time scales being considered. For example, if we are studying how wolves and field mice interact, we might find that wolves eat many more field mice during the day than they do at the night. However, if we are interested in how the wolf and mouse populations behave over a period of years or decades, we can average the number of mice eaten by each wolf per week. We ignore the daily fluctuations. We've already noticed that autonomous equations have slope fields that have a special form. So what this is talking about is that, do they have another? They don't have another picture of it, but here we can see here. This is autonomous. That slope lines along autonomous differential equations don't change with respect to t. So that means that like the slopes along a horizontal line are going to be all identical. Okay, so because the right-hand side of the equation does not depend on t, the slope marks are parallel along horizontal lines in the ty plane. Yes, the slope marks are parallel along horizontal lines in the ty plane. That is, for an autonomous equation, 2 points with the same y-coordinate but different t-coordinates have the same slope lines. All right, there's a great deal of redundancy in the slope field of an autonomous equation. If we know the slope field along a vertical line, t equal to t0, then we know the slope field for the entire ty plane. Right, that's an interesting point. That's true. So instead of drawing the entire slope field, we should be able to draw just one line containing the same information. This is called the phase line for the autonomous equation. Metaphor of the rope. Suppose you are given an autonomous differential equation of the form, okay. Think of a rope hanging vertically and stretching infinitely far up and infinitely far down. The dependent variable y tells you position on the rope. The function f of y gives a number for each position on the rope. This is the slope. Suppose the number is actually printed on the rope at height y for every value of y. Okay. Suppose that you are placed on the rope at height y0 at time equal to 0 and given the following instructions. Read the number that is printed on the rope and climb up or down with the velocity equal to that number. Climb up the rope if the number is positive or down the rope if it's negative. Okay, I don't get why this metaphor is any more than... Anyways, as you move, continue to read the numbers on the rope and adjust your velocity so that it always agrees with the number present. If you follow this rather bizarre set of instructions, you would generate a function y of t that gives your position on the rope at time t. Your position at time t is equal to 0 is y0 equal to y of 0 equal to y0 because that is where you were placed initially. The velocity of your motion at dy dt at time will be given by the number on the rope, so f of y of t for all t. All right, hence your position is a solution that, yeah, I don't get why you need this rope analogy. I mean, the math itself was pretty basic. The phase line is a picture of this rope. Because it is tedious to record the numerical values of all velocities, we mark only the phase line Hold on, I'm gonna take my jacket off. Okay, the phase line is a picture of this rope. Because it's tedious to record the numerical values of all we only mark the phase line with the numbers where the velocity is 0 and indicate the sign of the velocity on the intervals in between. The phase line provides qualitative information about the solutions. All right, let's consider an example. Okay, yeah, this is the logistic equation. 1 minus y dy dt is equal to 1 minus y times y. So we're going to have two solutions, right? We're going to have y is equal to 0 and 1 as our equilibrium solutions. Therefore, the constant functions are these two. We call the points y equal to 0 and y equal to 1 equilibrium points. Okay, so we're just trying to generate this picture. We also note that f of y is positive if y is between 0 and 1. That's because we're going to have like 0.5, for instance, times 0.5, which is greater than 0. So the slope is positive, and it's negative otherwise. Okay, so then we can draw the phase line or the rope by placing dots at the equilibrium points. And for the area where it's positive, we put an arrow up because the slope is positive. And then for y less than 0 or y greater than 1, we put arrows pointing down because f of y is less than 0. If we compare the phase line to the slope field, we can see that the phase line contains all of the information about the equilibrium solutions and whether the solutions are increasing or decreasing. Information about the speed of increase or decrease of solutions is lost, but we can give rough sketches of the graph of solutions using the phase line alone. These sketches will not be as accurate as the sketches of the slope field, but they'll contain all the information about the behavior of solutions for t goes to infinity. Okay. How to draw phase lines. Draw the y line. We can give a more precise definition of the phase line by giving the steps required to draw it. For the autonomous differential equation, dy dt is equal to f of y. Draw the y line. Find the equilibrium points, then mark them on the line. Find the intervals of y values for which f of y is greater than 0, and draw arrows pointing up, and then similarly for down. Here's several examples. Do they have a node? Let's see, do they have a node? Down, up, down, up, down, up, down, up. None of these are nodes. Okay. How to sketch phase lines. How to use phase lines to sketch solutions. We can obtain rough sketches of the graphs of solutions directly from the phase lines, provided we are careful in interpreting these sketches. All right, this sort of information that phase lines are very good at predicting is the limiting behavior as t increases or decreases. Consider the equation dw dt is equal to 2 minus w sine w. The phase line for this differential equation is given. Note that the equilibrium points are w is equal to 2 and w is equal to k pi. For any integer k. Suppose we want to sketch the graph of the solution w of t with the initial value w0 is equal to 0.4. Because w is equal to 0, Because W equal to 0 and W equal to 2 are equilibrium points of this equation, and 0 is in between those, or 0.4 is in between those two solutions, we know from the existence and uniqueness theorem that it's going to stay in between those. Moreover, because 2 minus W sine W is greater than 0 in that range, the solution is always going to be increasing. Because the velocity of the solution is small, but it's close to 0, we know that the solution increases towards it W equal to 2. And if we run the clock backwards, the solution W of t decreases. It always remains above W equal to 0 and cannot stop, since because this is t goes to minus infinity, the solution tends towards W equals 0. We can draw a qualitative picture of the graph. All right, great. Cool. Likewise, we can sketch other solutions in the TW plane from the information on the phase line. The equilibrium solutions are easy to find and draw because they are marked on the phase line. The intervals on the phase line with upward pointing arrows correspond to increasing solutions, with the downward pointing arrows corresponding to decreasing solutions. Graphs of the solutions do not cross by the uniqueness theorem. In particular, they cannot cross the graphs of the equilibrium solutions. Also, solutions must continue to increase or decrease until they come close to an equilibrium solution. Hence, we can sketch many solutions with different initial conditions quite easily. All right. Interesting. These observations lead to some general statements that can be made for all solutions of autonomous equations. Suppose y of t is a solution to an autonomous equation. If f... All right, so there's some conclusions we can make about autonomous equations. So if f of y of 0 is equal to 0, then y of 0 is an equilibrium point, and y of t is equal to y of 0 for all t. If f of y of 0 is greater than 0, then y of t is increasing for all t, and either y goes to infinity or it goes to the first equilibrium point larger than y of 0. If f of y of 0 is less than, then it's the opposite. Okay, so there we go. Similar results hold as t decreases. An example with 3 equilibrium points. Whoa. All right, so we have this big differential equation with high degree polynomial. All right, if p equals 5, p equals 20, and if p equals 0. Yeah, what a weird graph. Okay, they just they do an example. All right, we can read this example. I don't care. All right. All right, they get the equilibrium points. Then they evaluate f of p. and they find it's negative, so it's going to be decreasing on this interval, and they find that f of p is positive on the other two intervals, or on these two intervals, and negative on this interval. So we can place the arrows on the phase line appropriately. Now, note that we only have to check the value of f of p at one point in each of these intervals to determine the sign of f of p. Okay. The solution p of t with an initial condition in the region, blah, blah, blah. The arrows point up in this interval, so p of t is increasing for all t, tends towards the equilibrium point p equals 20. As t goes to minus infinity, it goes to the one below it. Hence, p of t is always greater than p is equal to 5. If we compute the solution p of t numerically, we can see that it increases from p of 0 equal to 8 to p equal to 20 very quickly. But we can't tell from the phase line how long it takes. Okay, yeah, here we go. Warning. Not all solutions exist for all time. Suppose y0 is an equilibrium point for the equation dy dt. Suppose y0 is an equilibrium point for the equation, then f of y0 is equal to 0. We are assuming that f of y is continuous. So if solutions are close to y0, if solutions are close to 0, y0, the value of f is small. Thus, solutions move slowly when they are close to equilibrium points. A solution that approaches an equilibrium point as t increases or decreases moves more and more slowly as it approaches the equilibrium point. By the existence and uniqueness theorem, a solution that approaches an equilibrium point never actually gets there. It is asymptotic to the equilibrium point. The graph of the solution has a horizontal asymptote. On the other hand, unbounded solutions often speed up as they move. For example, dy dt is equal to 1 plus y squared. Has one equilibrium point, and it's positive for all other values of y. The phase line indicates that solutions with initial conditions that are greater than -1 increase for all t and tend to positive infinity. If we separate variables and compute the explicit form of the solution, we can determine that these solutions actually blow up in finite time. In fact, that's crazy to me that we have like a simple differential equation and it blows up like this. Okay. We can determine that these solutions actually blow up in finite time. In fact, the explicit form of any non-constant solution is given by -1 minus 1 over t plus c. We are assuming y of 0 greater than -1. We must have y of 0 is equal to, we must have -1, right, okay, they're just substituting for 0. -1 minus 1 over c is greater than -1, which implies that c is less than 0. Therefore, these solutions are defined only for t is less than minus c. Okay, yeah, so that's interesting. So we have dy dt is equal to, what was it? Y plus 1 squared? Yeah. So this leads to y is equal to 1 over minus 1 over t plus c. But since we assumed y of 0 is greater than minus 1, then minus 1 minus 1 over c is greater than minus 1 implies that c is less than 0. But for example, c is equal to minus 1. Okay. Then we have minus 1 minus 1 over t minus 1. So t is defined for minus infinity to 1. But if it's greater, why can't it be greater? Let's say t. Yeah, that's actually a huge downside of the phase line. Like, you really want to know if it blows up, right? These solutions are defined only for t less than minus c. But why can't they be greater than it? If, on the other hand, well, like, let's just plug in 2. And y of t is equal to minus 1 over 2 minus 1, which is equal to minus 2. So, oh, I think I see the problem, right? Because if, um, Okay, let me just figure this out. If we have y of 0 is less than -1, then -1 minus 1 over c is less than -1, which implies that -1 over c is less than 0. Wait, what? Okay, whatever. Let's just try the other example. dy dt is equal to 1 over 1 minus y. If y is greater than 1, okay, so for y greater than 1, y dot is greater than, y dot less than 0. If y is less than 1, right, okay, yeah. If y is equal to 1, then dy dt does not have, yeah, so the phase line has a hole in it. But that's what I don't get about these, because for any given initial value problem, don't you have one on the other side? Or, okay, wait. Let's just figure this out. So we have 1 minus y dy is equal to dt. We integrate and we get y minus y squared over 2 is equal to t. Maybe we can do 1 minus, yeah, we could probably do minus 1/2 1 minus y squared. So we multiply by -2, so we get 1 minus y squared is equal to -2t. Then we square root, and we get 1 minus y is equal to the square root minus 2t. So if t is greater than 0, we have a problem. Right? So y is equal to 1 minus the square root of minus 2t. Okay, so, but I actually want to double check that. Can we just get ChatGPT and integrate that? I'm almost positive that's right, but so what I got was plus c. 1 minus. I really need to like just go over this freaking all right, so I got y is equal to 1 plus or minus the square root of minus 2t plus c. Wait, how did I do this wrong? Wait, that's not right. I think this thing just did it wrong. That's definitely not right. That's wrong. If you multiply both sides by 1 minus y, then you get 1 minus y dy is equal to dt. I'm pretty sure that's not right. Like, what are they looking at here? What is it looking at? One plus or minus one. Where did that extra one come from? Um, how did I get that? Oh, the C needs to be in there. Okay. All right, so I got that. Um, okay, yeah. So for any given solution though, when when t when t is equal to c over 2, or for t greater than c equal to 2, then you're gonna get an issue. Okay. Yeah, okay. Oh, here we go. This is exactly what I guess what I'm wondering is that if you have a hole in a solution to a differential equation, are there ones where you can make a hole and still have it like come out on the other side okay? Okay, so the book is talking about this example, and it's saying that this that once the solution crosses y equal to 1, um, you can't cross over to the other side of the hole in the solution, because but is it are there differential equations where we can construct it with a hole but still have it like work out such that the solution can continue onto the other side of the hole and basically all the trajectories still line up on the other side. It's just for that one point that there's a problem, or is that impossible? To draw the phase line for the differential equation, we need to know the location of the equilibrium points and the intervals over which the solutions are increasing or decreasing. That is, we need to know the points where they're greater than 0, less than 0, or equal to 0. Okay, what I was talking about is the difference between a genuine singularity and a removable hole. Oh, okay. So that's cool. Okay. It actually wasn't. I thought it was a dumb question, but it actually wasn't a dumb question. All right. As we have seen that when drawing a phase line, we need to find the equilibrium points, the intervals on which it's oh my god, it's like how much is it going to repeat itself? Okay. Given their significance, it is useful to name the different types of equilibrium points and classify them according to the behavior of nearby solutions. Consider an equilibrium point. Hold on. All right. Given this, all right. So, all right. The punchline is okay. It's a sink if things go towards it. Um, it's a source. It's a source if everything goes away from it, and if it's a node if it's either plus on both sides or minus on both sides. All right, let's just get to the exercises, right? All right, actually, I wanted to read this section on linearization. From the previous examples, we can determine the phase line and classify the equilibrium points for an ADE from the graph of f of y alone. Since the classification of an equilibrium point depends on since the classification of an equilibrium point depends only on the phase line near the equilibrium point, then we should be able to determine the type of an equilibrium point, y0, from the graph of f of y near y0. If y of 0 is a sink, if y0 is a sink, then the arrows on the phase line just below point up, and the arrows just above point down. Since f of y must be positive, and negative for just larger. So a sink corresponds to this. Yeah. Okay, so these pictures show why if we took f prime of y is less than 0, then it's a sink, because for y less than y of 0, f of y is going to be greater than 0. And for y greater than y of 0, f of y is less than 0. Okay, great. Now there was an interesting point about this actually. So these pictures are pretty obvious about the greater than 0 and less than 0, but if it's equal to 0, you can't determine. And I was like, well, why the heck, if you had it equal to 0, would you not know it's a node? And the reason why you don't know it's a node is because let's consider the graph, or let's read what it says and then I'll explain my thing. This theorem follows immediately from the discussion prior to its statement. Once we recall, is blah blah blah. Okay, the analysis of this conclusion is an example of linearization, a technique we'll find useful. The derivative of f prime of y of 0 tells us the best behavior. Tells us the behavior of the best linear approximation to f near y0. If we replace f with its best linear approximation, then the differential equation we obtain is very close to the original. Okay, here we go. We cannot make any conclusion about the classification of y0 if f prime of y0 is equal to 0, because all three possibilities can occur. All three possibilities. I'm guessing it means source, sink, and node. So, so we have this really complicated differential equation. Drawing the phase line for this equation would be a complicated affair. We'd have to find the equilibrium points to determine the sign on the intervals between, and on the other hand, it's easy to see that y equal to 0 is an equilibrium point. I mean, this is already a bundle of work, but okay. Okay, so it's just, okay, but wait, hold on. Right. Right, if we took dy dt is equal to y squared, so that means f of y is equal to y squared. We have just a basic parabola, and then we take f prime of y equal to 2y, So it's 0 at 0, so that's what we're talking about. But the problem is this is actually a node. But if we considered dy f of y is equal to y cubed, then we get 3y squared. It's 0, but it's actually not the phase line for this is going to be a source. Okay, so yeah, you can have anything when it's 0. Okay, it kind of goes over that a little bit quicker than I wish it would, but that was an important point to me. Is if you consider f of y is equal to y cubed, which is an example here, then you get an actual source, even though f prime of y is equal to 0. So you're not always going to have a case like this when it's a node. How much longer is this section? Holy shit. There we go. Okay, a couple more pages. All right. Modified logistic model. As an application of these ideas, we use the techniques of this section to discuss a modification of the logistic population model we introduced in section 1.1. The pine squirrel is a small mammal native to the Rocky Mountains. These squirrels are very territorial, so if their population is large, their rate of growth decreases and may even become negative. On the other hand, if the population is too small, fertile adults run the risk of not being able to find mates. So again, so basically what it's saying is that there's at least 3 equilibrium points that we know about, and this has been pretty common in this book about population model fixed points. It's you have basically an upper bound at which you can't grow anymore. You have a lower bound, which is usually negative, which means that there's just you're kind of you can't find anyone to mate with, and then a 0 fixed point where basically if the population's 0, I mean, how are they gonna just spawn out of thin air? All right, we can if the population is too big, the growth is negative. Okay, so let's just say we have let's say we have an alpha. So if p is greater than alpha, dp dt is less than 0. If p is less than beta, then dp dt is less than 0. Okay, so the population grows only if it's between too big and too small. Also, it is reasonable to assume if the population of 0 stays 0. So, okay, great. Blah, 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 blah. Is this the whole model? All right, so here's what I would say. I would say our expression is going to be p times beta minus p alpha minus p. So that means, all right, so let's just say that uh, beta equals 10 and alpha equals 50, just for the sake of this. So we have p times 10 minus p times 50 minus p. So if p is, let's say 5, then we're going to get positive times a negative times a positive. So we're going to get a negative. Okay, so that's correct. Now if we're going to get, let's do Ooh, I did something wrong. Well, we could change this to be p minus 10, I think. So if we have p, so it's going to be p times p minus beta. So if p is 5, then we get a negative, positive times a negative to a positive. So that's changed, stays the same. Now if p equals 100, we're going to get positive times negative. So that checks out. Now let's try it at p equals 30 or something. 20. P equals 20. We're going to get positive, positive, positive. Okay, cool. So that checks out. So my model, let's see, does this look the same? I didn't put a, all right, we could put a gamma there. All right, so yeah, times 1 minus, this should be the same as n minus s, I think. I think I could be able to multiply both sides by s and we get n minus s. So n is the carrying capacity. Okay, cool. So I did it right. That's correct. Yes, because this is the carrying capacity. So this is my alpha, and then this is my beta. M. Okay. So this parameter is S minus M. Yeah. So that makes sense. So if S is less than M, then you add another minus sign into the derivative. Okay. So they probably just want us to give the phase plot. So this is the thing, yeah. So it's negative, and then it's positive, and then it's negative, and then it's 0. All right, let's do the exercises really quickly, and then we can move on to bifurcations, which is a pretty cool section. Okay, so we're going to just do sketching the phase lines. All right, so I'm just going to hammer these out. Okay, so let's just like speed run them. So what we're going to do is we're going to do equilibrium points. So y is equal to 0 and 2 are the equilibrium points. So let's just draw a line for our phase line. So this is going to be y. We're going to add 2 dots. So there's going to be 1 at 2 and 1 at 0. And then what we're going to do is we're going to evaluate, let's say, what is the slope? So what is f of y, where y is, so this is going to be 3y, y minus 2. Let me highlight this one just so that we know which one we're talking about. Okay, so in this case, we're going to compute for, let's do minus 1. So we're going to get minus 3 times minus 3 is equal to 9. So it's going to be positive for y. So the derivative is positive for y less than 0. Okay? Now we're going to try 1. So we're going to get 3 times minus 1 because it's going to be 3 times y minus 2, which is minus 3. And that's going to be negative, so it's decreasing. Then finally, let's do 3. We're going to get 9 times 1 is not, so it's positive. So similar, so what we are going to get is we're going to get a source from y is equal to 2. That's an equilibrium point, but it's a source. And we are going to get a sink for y is equal to 0. Now, also, let's just verify this. We're going to take the derivative of f of y. So, again, do any of these... So none of these... So all of these are autonomous. So that's one thing to note, is that all of this phase line stuff is really just dependent on the fact that they're autonomous differential equations, which is kind of a necessary thing. All right. So I'm just going to multiply this out. We're going to get 6... Or we're going to get 3y squared minus 6y. And we're going to take the derivative again. So we're going to get 6y minus 6. Okay, at 0, we're going to get minus, so f prime of 0. Okay, so the way to think about f prime is f prime is going to have zeros at our equilibrium solutions because that's where f is at 0. Wait. Or that's where the slope of f is at 0. Right, yeah, that's where the slope of f is at 0. So then we f prime of 0 is going to be equal to 0 minus 6, which is less than 0. Therefore, let's just think about this again. So we're thinking about a line crossing the y-axis. So that means that if we this represents f of y0 is equal to 0. Then we're going to have some y less than y0 where f prime is greater than 0. So that means, yes, that means that they're going to approach 0. So if f prime of y, this is the helpful thing, is like when you have this thing that you're given to memorize and you just always rederive it, then you don't need to remember it. You can just rederive it. So f prime of y less than 0 means it's a sink. So the equilibrium solution y of t equal to 0 is an equilibrium is a sink. Okay, and then similarly f prime of 2 is greater than 0, so it's a source. Okay, so the first one was a little bit slow, but we're going to try to speed run these next ones. All right, so number 2, we get f of y is equal to y squared minus 4y minus 12. So let's just quickly, we're going to do, we're going to factor it, y minus 6, y plus 2. So then we're going to have two solutions. We're going to have y is equal to 6 and minus 2. So in our phase line, we're going to have a minus 2 here and a 6. And now what we're going to do, I'm actually going to just right off the bat do the second derivative. So f prime of y is going to be equal to 2y minus 4. So at minus 2, because I'm guessing a lot of these, it's going to be easier to just do this. So f prime of minus 2 is going to be equal to minus 4 minus 4, which is less than 0. So this is going to be a sink, yeah. And so the other one is going to be f prime of 6, and we're going to get is equal to 12 minus 4 is equal to 8, which is greater than 0, so it's a source. All right, speed run is gaining speed. All right, number 3. All right, so cos y, f prime of y is equal to, is it minus? I always forget if it's minus or if it's just sine. Hmm. Yeah, it's minus. I don't know how you're supposed to remember that. I'm sure there's a good way to memorize that. So cos y is equal to 0 at pi over 2 and 3 pi over 2, I believe. So plus minus pi over 2. Yeah. Good. All right. So we have okay, so then all right, so what we want to do is we want to calculate minus sine of pi over 2. So minus sine pi over 2 should be minus 1, which is less than 0, which means it's a sinc. So the pi over 2 case is going to have arrows like this. So let's say this is a sword. Okay. All right, so that's going to be a sink, and this is going to be a source down here. So we're going to, so then the minus sine of minus pi over 2 should be equal to minus 1 is equal to 1 is greater than 0, so it's a source. Okay. All right, this one looks interesting. Number 4. F of W is equal to W cos W. So our zeros are going to be 0 and plus minus pi k, or k times, wait, what am I trying to say? It's going to be plus minus pi over 2 times k. Or pi k plus pi over 2. Anyways, 3 dots. Okay, great. So yeah, um so this one I'm just doing the second derivative thing again, or the f prime. So then we get pi over 2 is a sink, 0 is a source, and minus pi over 2 is a sink again. And let's just double check that. So f prime of minus pi over 2 is going to be equal to 0 minus, or it's going to be plus, wait. It's going to be minus pi over 2 times minus 1, because sine of minus pi over 2 is less than 0. No, it's yeah, it's less than 0, so it's a sinc. Okay, great. So we're done there. Okay, so we have one at 1, 0, and pi k. So pi k for all k and 1. All right, so let's just do that. So 5, we're going to have, so it's going to be 1 minus w sine w. So we have 0, 1, pi, minus pi. Okay, so the derivative of this is going to be, what is it, u prime v plus v prime u. So we're going to get, seriously, what is going on though? Why don't I have this? Shouldn't I have all this stuff? Yeah. I think it's probably just that did I never write calculus? Oh, I never wrote calculus in CAS 8. I think we have to do this. Sine, what is it going to be? Sine pattern x, I think that. And then we do, wait, I can probably just do this. Let me do, let's say, I'm pretty sure that comment characters work like this. If I do this, okay. So if I do, if I do power rule, it'll probably just power, yep, that looks right. Okay, so let's see, what other rules do I need? Product rule? Oh wait, we don't, oh, we do want this actually. We want the integer here, that's right. Then we want, okay, so let's just see if I copy this in. I should be able to just say D, oh, but you know what? Let's do this. Set delayed D, power, oh wait, no. Pattern X blank pattern. We're doing only first derivatives. I don't want to handle the list case of second derivatives, but we could is just as well do that. Pattern X blank Okay, is this right? This is so hard to read. I think we just want to set this to 1, right? Oh, whoa, that was weird. OS error? I've never seen that before, ever. All right, so if we do just DXX, damn it, why didn't that match? D pattern X blend. Oh, you know why? Because I'm stupid. Okay, that's what we want. Oops, God. Okay. Oh, there we go. Okay. So we have that. So now if I do, wait, I think I set this up. If I do times X, I get POW, right? What? Dude, I thought I did all this. What happened? Did I never, you know what I think happened? You know what happened? I need to do this. Wait, what's different here? Some lambda calculus tests. All right, I'll use these. Okay, then what is this? Okay, that's nothing. That's nothing. It's nothing. I think this Omega combinator actually recurses. All right, so I can do a. Oh wait. So let's just delete all this. Or wait. I should be able to just discard changes on this file. Okay. Yeah. All right. Try again. What? History, dude. Let's just discard changes there. All right. Okay, so we should have gotten a bunch of nice changes, and then I just wanted to put this here, I guess, or I don't know where to put it. I can just put it right here. Let's see, CT. Wait, what just failed? Oh, I hate how they print this, man. This is the thing about Cast 3 that was so nice, is that, God, this stuff is so stupid. Yeah, so wish these worked. All right, I really don't want to do this. I just want a D. Okay. All right, so we should be able to just run this now. Whoa. Oh, it's probably because it's still running somewhere. That's really annoying. Okay. So I should be able to just take D, run these in here, then do D sine X. What? Oh, because it doesn't know my fucking stuff. This is probably wrong too. Power of pattern x blank to an n. That's where the D ends. Okay. So I'm pretty sure I need these two. All right, so first I want to do times. That's pretty sick, actually. That's pretty cool. I wonder if I can just do that. There's probably like a... God damn it, I forgot to unmute. Okay, so wait, I want to do. I don't know how this is gonna work because I feel like there's still missing. Oh wait, you know what I should do? Um, I don't have really a number for. So what I want to do is set delay. Wait, what is the head of X symbol? Head of 3.5 real. Is that what they actually use? So I should be able to do, even though I don't have alternatives and predicates and all that stuff, I should be able to do set delay D. Uh, can't I just do blank um real of pattern X blank and then just do 0? Can't I just do this? Then I do D of 5.5x. Okay, great. And then we just want to do this for integer. All right, so even though we don't have an alternatives thing, we can still kind of get some. Okay, so if I do, all right, so let's get some real ones. So we want to do D of I really wish I had a Okay, so it's gonna be a times plus 1 minus W. All right, so we don't have that rule yet. Yep, we do need chain rule, but right now, this might be all I need, baby. All right, so we got a plus times plus minus 1. Oh wait, I think we can do this. I think we can do this, right? Okay, so it was 1 minus w sine w. So let me manually compute that derivative. So we're going to get 1 minus w prime, which is equal to 0 minus 1. So we're going to get minus 1 times sine w plus 1 minus w times cos w. So what I'm getting is cos w minus w sine w, or cos w, sorry. W cos w minus sine w. Maybe I'll keep that factored. 1 minus w cos w minus sine w. Is that the same as what I got, which is 1 minus w cos w. Holy shit, that's right. That derivative is right. Damn, dude, symbolic programming is just so sick. You can do just like the most basic stuff and then, oh my gosh. That's so cool. Like 19 lines of this code plus 1,000 lines of the actual programming language. And it's easy to write derivatives. That's all it takes. That's all it freaking takes. All right, so now I have. Oh, we actually need a sim on the end of this. Hey, what's up, Riley? All right, so we got the zeros. Yeah, so we should write this like this. It's been a while since I did this. All right, so x blank, we get the 1 rule. All right, here we got a times. Oh, do we have that? I feel like we get that for free from the product rule. Dude, calculus in Cassidy is so sick. You got a good setup now? So do I, bro. I got my microphone. What's your setup? Console and PC. All right, let me just do this last derivative. All right. Set delayed d exp. Oh, is that a chain rule thing? No, but shouldn't this be the same blank? How did I write it before? Oh yeah, you need a chain rule. All right, we're not going to run into any exp. We're good. But I agree. I think I do. But the generic chain rule. I think that's right, actually. Is that not right? So if we have, let's say we have f of x, and it's d f of x to z. Then can we not do df dx times dx dz? You use a Bluetooth headset. I'm going to ask ChatGPT. That's cool. I forget how this all works. That's fun. I want to test if in an expr, basically, all right, yeah, let's see if that works. All right, so we got the chain rule, right? All right, so the derivative of, all right, so we have f of x is equal to sine, wait. The whole expression is sine of x squared. So f is equal to sine. Yeah, so f of u is equal to sine u. And we're plugging in. So then df du is equal to cos u. So now we need cos u d cos u d. Hold on. Oh, wait. Okay, wait. First off, this is wrong. Wait, is it wrong? Yeah, chain rule is harder. Because this is totally malformed expression. Yeah, I wonder how they do that. The fitness gram pacer test. Do you guys do that in Louisiana? I remember doing that. Hmm. I think perhaps I need to do this. Let me try that. No. Yeah, so we have. The derivative of f of x with respect to z is equal to df of x dx times dx dz. That's the chain rule. And the chain rule, so why isn't this working? So, okay, so wait. F is the symbol. Oh, wait. I think I see what's going on. I think I see what's going on. Because the problem is F. First off, it's crazy that this is matching. I feel like this shouldn't. Or no, this will match. This will match, but the question is, when I put in f of x, it's weird to me. See, this x is right. Okay, wait, let's try this. D sine of times xx times xx. So I believe that's right. I'm pretty sure that that's a correct derivative. Let's double check that. No, I never play that game. Why? Raleig's Crack House? Dude, aren't you like 10 years old? What the hell? All right, so I'm pretty sure that's correct. I'm pretty sure that this is right. Now, the question is, why? What rule are we hitting where. Dude, I'm not going to look that up. Not on stream. Oh, man, I'm so close. I really want it. I really want it. I don't. Oh, you know what? Wait, hold on. No, this has. Oh, shoot. Hold on. Shouldn't this recurse on the same rule as before? So if we did like set f to uh okay, Damn, I'm so close to having chain rule working. I think. I think chain rule is really close to working. So we have this function call here, f of x. And we're taking the derivative of f of x with respect to z. Okay, wait, you know what I want to do? I want to do this, and I just want to see what happens. So we should get back. So I want to make sure that the rule is right. Because if I do this, so what we should get is this should just give us 2x. Okay, so something weird happened, right? Because let's look at what happened here. Wait, is that the same as above, though? See, that's why I think that this is not the rule being applied. This is why you need something that, like, traces what rule gets applied. Because otherwise we have all these issues. Because I don't think that we got this rule. Because if we look at this, it probably dispatched on... Oh, it definitely dispatched on this rule. Did it not? Maybe it didn't. No, it definitely didn't, because that's not a match. If we did this, so we did... Hold on. So we have this, and then we call them match Q this. Should be false. Oh, but it's true. But it shouldn't be, right? Oh, wait. No, wait, I got the wrong one. Okay, so that is true. But that's good. That's what we wanted. But this one should be false. Yes, dude, I'm so sick. Gosh, symbolic programming is the coolest thing ever. All right, what if I just return X? Yeah. But why? Because... All right, let's do this. So all these are good. These should be good. All right, I just want to see if we're going to get a match on this. So I want to do d of sine of times xx x. Okay, great. So now I want to revert back to what we had. So this is going to be times d fx x dxz. And that should be the chain rule. So now we overwrite this. Oh, wait, you know what? I think it's... I think that we might just have an issue with overwriting rules. I wonder. So if I do, oh wait, actually that might work. Oh, I have to do that. Isn't there a way to like page the previous results? Whatever. D, oh wait, you know what I can do? I think I do D sign, whatever. I don't care. Holy hell, dude. 2x, yeah. And some basic simplifications, we can just do this. Set delayed power blank. Oh. Um. Okay. I don't know if this is. I think that should be fine. Bro, look at my chain rule. Look at my freaking chain rule, bro. That's the chain rule, son. That's the freaking chain rule, dog. That's so sick. Okay, now I want to do. You know what? How do I just page? Oh, no, wait, hold on. Now that's interesting. A stack overflow when I try to take the derivative of the exponential function. That's interesting. All right, at some point I gotta call this and just start doing my actual homework, but this is so freaking cool, man. I'm guessing that this chain rule is too generic and because the problem is it's gonna keep calling this, and we need to cage it out because if it's gonna recurse on, so maybe I don't know, maybe hold on, let's try this. Maybe if I put these rules up above the chain rule, then maybe they get like priority. Although I just don't remember how I did all this. It was so long ago. Or if I do this, this probably still overflows. Okay, it doesn't. All right, so maybe the order did matter. All right, now let's do D, X, X, Y. Let's make sure that. So that seemed to chain rule. But that doesn't seem quite right. That probably shouldn't match anyway, right? Actually, no, I think that's true because if y was x, then that would evaluate to 1 and then everything would simplify out. So maybe that is correct. But my guess is that what Mathematica does is that it leaves it unevaluated. So if we were to check for parity on that, we'd probably fail. But I'm pretty happy with that. That is pretty fucking cool. All right, I'm gonna be right back. I'm gonna take a piss. But now I have calculus kind of working on Cas 8, which is nice because um now I can use it for homework and I don't have to like I don't know. The thing is I really wish I had implemented like a Sixel type of. I mean, Sixel doesn't work on Windows, unfortunately, or Windows Terminal or whatever. But it would be so cool to have an output form. Output form is basically the output form. Basically, is like basically. I mean, the design of this language is just so freaking beautiful because basically all it does is whenever you evaluate an expression in the REPL, you call this thing called output form on it, and you can do all this stuff that like output form could instead of returning like the expression, it returns a view of the expression that's like pretty. I don't know. The design of this language is just so good. I mean, I'm just copying it all. I'm just stealing it straight up. But like, damn, if it wasn't like $500 a year or whatever, I would totally get this. All right. I want to try that even harder example. Let's try that one last one, then we're going to get back to it. Dx sine x squared. Let's fucking do that. Oh, wait, but I need to write that in my form. Okay, so it's going to be dx sine times xx x. Oh, come on, baby. Damn it. Yeah. I knew it. I knew it. It's okay. That stinks, bro. Because stuff that self-evaluates like that, you gotta be really careful. Okay, so for the first expression that's going to be made is going to be dx of I really wish I implemented um, trace. I don't know how to do that, but trace is so cool. Then we're going to get times, and then x in this case is sine x squared with respect to z, which is x. So this is going to be... So it should be x sine x squared times 2x what is it? 2x cos x squared? I don't remember what it was. I wonder if they just do a rule for like everything. I can't imagine they do. If they just had a ton of rules, it wouldn't be generic enough. It definitely has a chain rule, but I just don't know how to avoid this infinite recursion on the exponential. The thing is, it shouldn't be recursing infinitely because all right, so the expression that we're trying to do is we're trying to do d of x of sine of times of x times x with respect to x. So this is the derivative that we're trying to take. Now, I'm pretty sure if I run this rule, I'm going to get d of sine times x with respect to x. I'm going to get the correct answer here, which is, wow, it seems like that doesn't always... Wow, that's so weird. Did you guys see that? I've never seen that before, ever. That's crazy. It's non-deterministic evaluation. What the fuck, dude? That's nuts. I don't even know how that happened. I didn't think that was possible. Non-deterministic evaluation. That's crazy. What the hell, dude? I mean, it's the same expression, but damn, that's so weird. How is that happening? Oh, that's so interesting. Is there a pattern to it? I don't know. Kind of seems like a coin flip. That's so weird, dude. Okay, so anyway, so if we think about this, so we get this right because it's 2x cos x squared. Okay, so let's think about this. So if we do dx, right. So that's correct. So I actually don't know how this overflows. Wait, I thought it overflowed. What happened that it overflowed? That's correct. 2x cos x squared. Wait, why doesn't that work? I probably commented out. Wait, am I stupid? What the hell? I guarantee you, dude, I'm stupid. So that's an expert. Yeah, I should be setting all of these because I'm sure that they do. But whatever. I mean, how much are we gonna do here? All right, I just want to see if this works. This would be so cool. You know why? Because this, I'm not really taking into account the flatness thing. I wonder if I can do. Okay, so if I have like a pattern x's blank sequence. I'm pretty sure I could do like a map, like a map. Let's see, how do I do map f list 1, 2, 3? So I'm pretty sure I could do, but I don't want to list. Oh, you know what I could do? I think I can do. Can't I do? Oh, you know what I could do? I could do apply times. Yeah. So that's what you need to do. You need to apply times map f args. So if we want to make this generic, we would do this would be blank sequence. I want to see if this will work. This would be really cool. So we get D, so it's a sequence of things in the times. And what we want to do all right, wait, let's what we want to do is we have all right, wait. Wait, let me undo that. And let's just delete that. That works though. That's cool as hell that that works. Dude, how much of this am I gonna do? We're like two and a half hours into this. All right, let's just get this thing down. So this is gonna be a blank sequence. So what I want to do is I want to do like a set delayed dd. Let's do dd times pattern x's blank sequence. And then it's going to be a pattern z blank. Okay, so then what we're gonna do here is it's gonna be equal to an apply plus, because on a oh wait, actually this one's hella hard. If you have f of x, g of x, h of x, if you have three things, the product rule becomes way harder. That's actually interesting. What's the product rule for more than two? Because it should be some weird thing where like you have to compose, or you have to like not compose, but you have to like juxtapose them. So you have to like let's say f equals f, but then f2 is equal to g times h. Then you do that, but then you got to plus them. But I guess okay, so more okay, let's just do this. Let's do it on plus, because plus doesn't actually have really crazy semantics. But so plus on a blank sequence, we're gonna so first off, let's just do map. Oh, and we might have to do like a how are we gonna define this function? Because what we want is we want x to dx, dxz to x's. That's what we want. But I don't know if I can do that. Let's try this. You know what? Let's just try it. So it's gonna be a function x dx z to x's. And x's should have a list, right? Well, I think it's a sequence, but map on a sequence might not work. Let's try dd of plus 1x times xx x. Well, that's obviously wrong. 1 plus x squared. It should be 1 plus 2x. So what went wrong? I'm pretty sure. Because what is. You know what? Let's do this. Set delayed foo. And this is going to be a pattern x's blank sequence. And all it's going to return is x's. The problem is I'm thinking. I'm pretty sure that that the sequence splices. So if we do this, I don't even know if this is going to be a good, like if we do foo 1, 2, 3, oops, we're getting a sequence. But I wonder if I do apply list. Wait, apply list. No, you know what I think all I have to do? I think I just have to delete this. I think I just have to do this. So I think maybe we should be able to just do list. And then we're going to try DD. No. God damn it. I really thought that was going to work. So we have a... Okay, wait. So hold on. Let's just say we have a... All right, so we have, let's say X set X sequence. I don't know if this is going to work because I haven't. Okay, so on a set, it must be a sequence hold or something. Let's see, attributes of sequence, or no, of set. Yeah, so set is sequence hold. So that makes sense. That's actually good. Wow, dude, they designed this just so smart. Oh, it's just so cool. All right, so that's good actually, and I'm sure that it's the same on a set delayed. Yeah, so that's good. So what do we need to do? We need to do a thing where we're like um um so we want to call the right hand side. So we want to call map function x dxz. What is z? Z is just going to be, ugh, see, this is actually stupid. My function is so bad because what we call this matters. So function foo d foo x of list x. Oh wait, can we have x equal to... Oh, you know what? I think I'm just hitting this stupid reevaluation bug. I really need to fix that. Right, so now we just need to do a apply plus. All right, cool. So I think we have something that is generic on the plus. So this one is no good. We need to like... I wonder if this works. Does this... I'm pretty sure that my parser is strong enough for this. But I don't know, does there need to be those spaces in there? I don't know. Okay, if I do this... Okay, nothing happens. Okay, so I think we have our thing though, right? It's where is it? Where's our blank sequence? So it's going to be this. Set delay D plus pattern X is pattern Z. Map function X dxz. So now the problem here, I think this is going to get really messed up. I think this is going to get really messed up. Oops. Oh, God, this thing is so stupid, man. Hold on. Dumbass camera. I should just get a new webcam. I think it comes back alive almost every time. Is it going to? This thing is so fucking stupid, man. I don't know why it does this, man. Okay, well. All right, let's just try. I don't really care about the camera right now. I just want to see if we can get any example of this to work. So I think all we need to do is do an apply plus on the map. So I think that is the correct thing. The only thing I'm worried about is the fact that oh, yeah, so here's the problem. So I mean, this is God. Yeah, so what needs to happen is the problem is that the lambda over foo is going to capture z if we happen to try to take the derivative with respect to foo. So it's just a problem with my lambda. Dude, I really need to just write a full lambda calculus because then dude, lambda is just so powerful. Oh, I'm so happy about my webcam being down. Isn't that great? Okay, well, let's just try this. Okay, so I'm going to copy this over. Where's my plus? Here's my sum rule. This is a binary sum rule, but this is terrible. So we're gonna do this one, but we're gonna do this, and then I'm just gonna run it up to there because we don't really need much more than that. So we're gonna do this. Okay, and now I'm gonna do d of plus 1 x times xx with respect to x. What's us? Oh, you know what? I must have misspelled something. Where's my sum rule? Oh, jeez. Apply PL to U best. That's great. I'm guessing that this is not going to do what I want. Okay. Let's just write it again. All right, so we got D plus 1 x times x x. No shit. That's pretty freaking cool. Okay, so I think modulo a. But yeah, I really I wonder how we're gonna handle this thing. What is the product rule? Wait, I can just ask. Yeah, that's what I thought. See, this is kind of where I always bottom out or cap, I cap when I when it comes to writing like mathematical like code. Like the symbolic stuff, it really works for certain things, but then it's like for this, I would love to write imperatively. I'd love to just like, I don't know. The thing is, loops aren't that hard to implement, but I'm just opening up a can of worms, and then I'm not going to be in spec, and then all sorts of stupid stuff occurs. Um, all right, let's just let's just get back to doing the homework. Um, I am gonna fiddle with this thing, I think. All right, okay. Um, 1 divided by. I don't think we did quotient. I don't think I did quotient rule. This mic stand's pretty sweet. I like it. Okay. All right, let's just read them. I'm not going to do them, but let's just read them. All right, so we did these. We get it. We get an initial condition, sketch the graphs of the solutions. Okay, that's basically the same thing. Okay, so we're going to use these equations up here, and we're just going to plot them. Ooh, that one might be cool. A trick question. I don't know. Trick question might be fun. Describe the long-term behavior of the solution to the differential equation. With a bunch of different initial. Okay, so that's cool. Let's see. So that's gonna have 2 roots. So I don't know. Most of these are gonna be the same, I think. Um, maybe it doesn't have 2 roots. I need to think about that. Consider the autonomous differential equation. Um, suppose we know these two. Okay, I think I didn't I do this one? Wasn't this in like the last section? Okay, so we don't know that this isn't in equilibrium. So this could be in equilibrium, or it could go to -1, or it could go to 2, but that's pretty much it. Suppose also that f of y is greater than 0. Okay, well, it has to go to 2 then. Okay. right, so the phase line here, so for this one, we're going to have a line. Here, I'll do it here. We're going to have two dots. Then this bottom dot is going to correspond to this root, and it's going to be a sink. Because if y is greater than this y0, this root, then the derivative is negative and it's going to flow back to it. And this one is going to be source. This, we got a... Let's look at that picture again. There's a very good picture here. So this is what a sink looks like, and this is what a source looks like. So here we're getting a source. Here we're getting a sink. Okay, node. This is going to be a source. This is going to be a sink. Yep. So sink, source, node. Sink, source, node, sink. A phase line for the autonomous differential equation is shown. Make a rough sketch of the graph. Okay, so this is going to be, we're going to have a line going across here, and this one's going to go up like that. This one's going to go down like this and like level off here. And then this one is going to come from infinity, minus infinity, and come up and level off on this equilibrium. So this is a sink, and this is a source. And so then we get... And then we're going to have, two lines coming across. Here we're going to get line, 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 line. And it seems like we got a node here. So in this case, a node, the solution is going to come and level off. And then it's going to also go down and level off here. And then this one's going to come up here. And then this one's going to come and level off and go up again. This one is going to go up to there, and this is going to decay to minus infinity. All right, we get the idea. 8 differential equations of 4 phase lines are determine the equation that corresponds to it. Okay. All right, so we have y, 1 minus y. That's this one, number 2. So y, 0, 1. So it could be this one or it could be this one. It can't be any of these because there's more, but I'm guessing that 2 is one of these. So the question now is if we have... I'm pretty sure that it's A, because for y, 1 minus y, if y is greater than 1, then we're going to have a negative on there. Wait. Yeah. We're going to have a negative there. So then, okay, so 2 goes to A. All right, so we get the idea there. Are there any harder ones? I think that's pretty much it. Oh, but this could be y squared times 1 minus y. If it's 2, this is going to be 8, and this is going to be 4. This is going to be negative. I think that this... That's going to be an interesting one. Maybe we could do that one. Let f of y be a continuous function. I think we did this one. I remember this model. Ugh. Um, fuck. Um, I don't want all that. I don't want all that. Oh, I did this one in class. This one was nuts. All right, so that's 1.6 with a detour on how to compute derivatives symbolically. Peace.